In lab 9.4, you will be creating a precision clock divider that will drive a 6-symbol binary coded decimal counter. Okay? So to begin with, one of the things that we have from the prior lab was that we had a need to divide the clock. Okay? Into our FPGA board, the DE0CB, comes a 50 megahertz clock. And that's great if you're just doing real-time data processing where you want to go as fast as possible. Not so great if you want to observe anything with LEDs. Okay? So specifically, if you think about the character displays, if you want that thing to count, like actually count time, like every second, 50 megahertz clock, you can't just run your counter directly from that because it's too quick. So we had this need to divide it down. And what you did last time was you created a 2 to the n clock divider. And that used a ripple counter configuration in order to continually divide down the clock using toggle flops, and that worked fine. It was very simple. The only issue is that you couldn't get every frequency that you wanted. You could only get frequencies that were multiples of 2 to the n, or dividers by 2 to the n. So you got 25 megahertz, 12.5 megahertz, 6.25 megahertz, et cetera, et cetera. We can, however, at this point, use our knowledge of counters and range checking in order to create a more precise clock divider, which we can call a precision clock divider. Okay? So let's take a look at how we might think about this. We have a clock that comes into our system that is 50 megahertz. Okay? And if you think about what the period of a clock is, it is 1 over the frequency. Okay? So this is the frequency of our square wave coming in. And the period of that is going to be 1 over frequency, 1 over 50 megahertz, and it actually comes out to be 20 nanoseconds. Okay? Now, what does that mean when we look at it with a signal, or look at it on a waveform? If we had our clock coming in, what it would look like is this. We would have this clock that's going along here. Life is good, 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 life is good. Okay? And it's hammering away, and it's just doing its thing. Okay? The period of the clock is always defined, the period of any wave that is periodic is defined as the time difference between like edge to like edge. So in a clock, it's either rising edge to rising edge or falling edge to falling edge. It'll be the same thing. But every 20 nanoseconds, we get a clock period. Well, we could use that to drive a counter. And then what we could do is we could potentially use range checking in order to count up to some value that we know, okay, some amount of time that we know, and then use that range checking to do something to a divided down clock such as toggling. Okay? So let's do an example where I want to create a 5 megahertz clock. Okay? So I want to divide this down and create a 5 megahertz clock. What I can think about is what is the period of a 5 megahertz clock? Well, it's going to be, let's see, is it, let's do the calculations. Everybody know off the top of their head? 200? Okay, so you're right. So it's 1 over 5 megahertz, which is 200 nanoseconds. Well, let's draw that compared to this dude right here. So if I think about this is going to be my clock div, okay? We could say that it starts right here, and we go like, here's 20, okay, here's 40, here's, let's think about that, here's 20, here's 40, here's 60, here's, let's draw a little line down here so we can actually see it. So here's 40, here's 60, here's 80, and here is 100, okay, and then over here is 120, over here is 140, and we'll have to take this out just a little bit further so we keep our 50 megahertz going. So then here is 160, and then here is 180, and then finally here is 200. Okay? But when you actually draw that out, that's not when it toggles, right? 200 nanoseconds is one cycle. So it actually kind of goes like this. It would actually kind of start off where you'd say, if this is it, I'm going to go out to 100, and then I'm going to go up, and then I'll go over to here, and then I'll go down, and then I'll go like that. So this right here is going to be the period, which is going to be 200 nanoseconds, of the clock I'm trying to create. But what's interesting is that we could actually define this in terms of multiples or counts on the incoming 50 megahertz clock. So for example, notice that this is really one cycle here, which is 20 nanoseconds, 2 cycles here, 3 cycles here, 4 cycles here, 5 cycles here, and then we toggle the clock. And then it's 1 cycle, 2 cycle, 3 cycle, 4 cycle, 5 cycle, and then you toggle the clock. That was a little out there. What if we did the following? What if we used our 50 megahertz clock and we drove a counter? And a counter just like you've done at this point. A one process counter, and all we're going to do is count up to some value and then flip back to 0 and count up again. What would it look if we wanted to set a range of a counter that matched when we wanted the clock to change its logic level? Well, if you think about that, let's start off by doing this. So we would have, if the clock right here was 0, then it went up to 1, then it went up to 2, then it went up to 3, then it went up to 4. That is essentially 5 clock cycles. Would you agree? This is a counter. You're driving a counter, and it's going to count 0, 1, 2, 3, 4, back to 0. 0, 1, 2, 3, 4, back to 0. Well, what's neat about that is that this also, 0, 1, 2, 3, 4, back to 0. So our counter would actually look like this. So we know how to do this. I mean, this is not that hard. This is simply range checking. So we could put a range on this that said, I want an integer counter that does nothing more that counts up from 0 up to 4, 0 up to 4, 0 up to 4. It gets up to 4, you check. Is the thing 4? Yeah. If it is, instead of incrementing to 5, set the puppy back to 0. Okay? We've done this multiple times now. You know what else you could do? Every time you hit that range, you could have an internal signal, maybe called clock div, that you could complement. What would happen if within that same process that you do these range checking, you came down here and said, you know what, I'm going to have clock get assigned not clock. What would happen? You would generate a clock that would toggle every 5 counts. That's pretty sweet, because if you think about it, we now have created something that has a low time of 100 nanoseconds and a high time of 100 nanoseconds. That together is 200 nanoseconds, and that is indeed a 5 megahertz clock. Isn't that pretty sweet? So this is now considered what we call a precision clock divider. The reason it's precise is because you can get a period, a toggle period, that is within one period of the incoming clock. So you could get within 20 nanoseconds of having a transition. Okay? All right. So how does that feel? It's like, okay, that's kind of cool. Let's do one more example that would make it a little bit more meaningful. Okay? This will not change. That is the crystal on the DE0CV. You cannot change that. What you can change is the range that you will check against. Let's say that I wanted to create a 1 kilohertz clock. Okay? If I drew that out, I would sketch it out, and it would look like that. The first calculation that I would like to make is I would like to know the actual period of that clock. Well, that's nothing more than 1 over the frequency, 1 over 1 kilohertz. And let's just make sure we have our numbers. So I'll do this on a calculator here. So I'll go 1 divided by 1 divided by 1,000. 1 divided by 1,000. Okay? So that is 1 millisecond. Okay? Tell me the time, though, if we're going to use this precision clock divider approach, tell me the time that I actually want to care about when I toggle the clock. It's not toggling every 1 millisecond, is it? No, it's actually toggling at half of that. So right here is really what we care about. This is going to be 0.5 milliseconds, and then this is going to be 0.5 milliseconds. So that's important because if I use this clock gets not clock, what I really want is to create a counter that will count for a certain amount of time up until it gets to a count that is equivalent to 0.5 milliseconds. So logically, what we need to do is we need to calculate, if I start here at 0 as a counter, what am I going to count up to that will take 0.5 milliseconds worth of time? Okay? So you actually do it just by saying the number of counts that I'm going to count up to is equal to the amount of time that I'm waiting, 0.5 milliseconds, divided by the period of the 50 megahertz clock. So that comes out to be 20 nanoseconds. Okay? So I have 20 nanoseconds. Now, what does that count come out to be? So I'll take this. This will be fun. Divided by 20 exponent. What's a nano? It's a 9 negative. And the answer is 50,000. Now, does that freak you out? It shouldn't freak you out at all because it's just a count. All it is 50,000. Before we were doing a counter that would count up to 15, and we did it with integers, right? So we just counted up to 15 and went back down. Yes?
Did you divide 1 millisecond by 20 nanoseconds? Yeah. 0.5 milliseconds?
I want you to think about something here. Oh, what did I do? You're right, you're right. Let's do this. 0.5 exponent 3 negative. You can't. Okay, there you go. You're right, you're right. Divided by 20 exponent 9 negative. It's 25,000. You're absolutely correct. 25,000. Okay. I am going to count from 0 up to 25,000, and then I'm going to flip back to 0. Okay? Actually, it's going to be 24,999, but you're within 20 nanoseconds, so you could just do 25,000 if you want. But I count, and that's going to give me 25,000 counts. I'm going to range check my counter back to 0, and then I'm going to count again up to 24,999, and then I'm going to range check, go back to 0, etc., etc. In that process, I am also going to have some signal that I'm going to call a clock divider or whatever that I'm going to complement. I'm going to do this count gets not, or clock gets clock not, and that will toggle, and look at what I've done. I've created a slower clock that is precise within 20 nanoseconds of what we're trying to get. Okay? Now, this is beautiful. So here's what we are going to do. The first part of lab is this. You are going to create a precision clock divider, and while we're doing this, why don't we also make it selectable? You are going to create a precision clock divider that will produce 4 different frequencies. 1 hertz, 10 hertz, 100 hertz, and 1 kilohertz. Okay? These are now nice numbers. Okay? We're going to use these. 1 hertz, if something's counting on your DE0CV board, it will count in real time. It will count 1001, real seconds. Okay? 10 hertz is fast enough that we can have a larger counter and it'll go a little bit quicker. We need 100 hertz to see larger digits of a counter, the larger bits or upper bits of a big counter. And then we need a kilohertz in order to really, really go fast so that we can have it actually do something. Okay? Here's what you're going to have in terms of the entity for this thing. Okay? You are going to have a new entity that you will create called clock underscore div underscore PREC. That stands for precision. It is going to have an identical port definition as your clock divider 2 to the n. You could consider copying it. Okay? But this is a separate file, and you will have a clock coming in, obviously a reset. You will have 2 bits of select, which will choose amongst the 4 clock frequencies, and then you will have a clock out. You will create a process that is going to be a counter, and you will range check in order to achieve these 4 clock frequencies. Okay? Now, how are you going to do this? Some strategies. You've got 4 clocks that are going to be selected amongst. How do you select amongst 4 different clocks?
You borrow the multiplexer design that you did last week.
Yeah, you could do this a couple different ways. Number one, you could use your multiplexer to select amongst 4 clocks. And you could absolutely make 4 unique clocks. Make 4 processes. Each of the 4 processes creates this. It would be copy paste, piece of cake. Yes?
Could you also just divide down the same process?
Or you could have one process that generates the clock, and you would change something based upon the incoming select lines. What would you change in a process with range checking to change when it's going to count up to, or the maximum value will count up to? Change the range. So you could conceivably put some logic within your process to say, if select is equal to 0, 0, then my range will be whatever, 100,000. If select is 0, 1, my range will be 50,000. If it's 1, 0, it'll be 25,000. Okay? That is nothing more than just an if-then statement that you could have in there. So you have 2 options. The flexibility is up to you. You can either create 4 different processes, each generating these clocks, and run it through a 4-to-1 multiplexer, very similar to what you did with your 2 to the n divider. Or you could create one process and have its range that you check against dynamically change based upon the incoming select lines. So now we're getting to the point where you have a little bit of flexibility on the logic that you use. Okay? But that's not it. That's part 1. Part 1 is then you're going to take that clock divider, and you know what you need to do? You need to take it and make sure that it works. So you are going to route that out to pin D0 on the GPIO1 header, and you're going to take an oscilloscope measurement. Okay? And we haven't done an oscilloscope measurement on chapters 8 or 9 yet, or labs 8 and for chapter 8 and chapter 9. You're actually going to measure the frequency of this, and you want to be able to change your select lines and make sure that you can change between 10 hertz, 100 hertz, and 1 kilohertz, and even 1 hertz. Okay? That's part 1. That screenshot is going to be your deliverable. All right. Now, the next step becomes, let's use that to drive some counters. Okay? But what we're going to do is we're going to do what we call a BCD counter. That stands for binary coded decimal. And it's really nothing that fancy. All it really is that we know that if I'm a binary counter, I'm 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and I can count up to 1, 1, 1, 1 before I roll back over. Okay? Not a big deal. In decimal, what is that equivalent to? That's equivalent to counting from 0 up to 15 and then back to 0. Right? Well, how do humans count? Most humans don't count in hex or in binary. We usually count in decimal. Okay? The only trick with decimal is this. You go 0, 0, 0, 0, 0, 0, 0, 1, but you get up to a value that is equivalent to 9, and then you go back to 0. So 9 turns out to be in binary what? I know that 10 is 1, 0, 1, 0, so it's 1, 0, 0, 1. Okay? You could create a whole bunch of crazy circuitry to handle this. Or you could create a process with range checking. Agree? All you're going to do is take that same process that's a counter that you've been using for everything now, and you're going to paste it in here, change the range to go from 0 up to 9, back to 0. Boom. You have now created a binary coded decimal counter. 1 bit. Okay? Not even a bit. 1 symbol. Okay? Pretty easy. Too easy, in fact. Let us now move up just a little bit higher in abstraction. I'm going to go away from the binary, right? The binary, these are binary. This is decimal, and this is decimal. Let us move down and think about counting in decimal now. So I'm a decimal person, and I count 0, 1, 2, 3, all the way up to 9, and then what do? I go back to 0. But if I want to count higher than 9, what do I have to do? I have to bring on another symbol, don't I? So I have to actually bring on 1, 0. And then I count up 1, 0, or 1, 1, 1, 2, and I keep going, At some point, I'm going to get to 99, and what do I want to do? I'm going to have to bring on another symbol, right? So I'm going to have to bring on 100. And then I count 101, 102, and I go all the way up to what? 999. And what do? I got to bring on another symbol. So I'm like, ah, man, this is cool. I can count, I can keep counting as long as I can keep bringing on symbols, right? Well, check this out. If I wanted to implement a really cool lab, I could actually do this on the DE0CV board because I have 6 symbols worth of display. So I could count from decimal 0.00000 up to 99999. That is 999,999. Almost a million. It's actually a million counts because if we count 0, but let's not get into that. Okay? I then ask you, you're throwing counters everywhere at this point. Single process counters with range checking. We're using it for everything. We already know how to make 1 symbol's worth of counter, right? That's easy. You know what the only thing about it is? I am going to create this counter that does this least significant bit using 1 process. Of course I am. Okay? I am going to create another counter, which, of course it was just sitting at 0 while we were doing all these counting. So this is going to be another process. Okay? The only thing that's different about this process right here, this process for like symbol 1, if this is position 0 and this is position 1, it increments, but not every clock cycle. When does it increment?
Every time the first process rolls back to 0.
Yes. It only increments every time this process gets to 9. So this is now a process that depends on another process. It's still a separate process, absolutely its own process. And it's going to sit there, and every edge of clock, it's going to look, and it's going to say, did I get a reset? Okay, I didn't. Let's go check if I got a rising edge of a clock. Did I get a rising edge of a clock? Then it's going to say, okay, should I increment? And do I increment every clock? No. I only increment when the buddy beneath me got to 9. So I have to look at this bit right here and say, did the lower position bit get to a 9? Then I will increment. Okay? What about this one? Holy moly. So I got a process that's sitting here, and it's just free running. That's process number 1. Okay? This is P1. I got this process right here that only increments. This is P2. It looks at this symbol right here. Oh my goodness. How do I handle the 3rd symbol? It is a separate process that depends on not only the dude below it, but it also depends on this bit too. And you go, why would it depend on 2 bits beneath it? It's because when you get down to 990, it doesn't increment. You still have to wait for it to go to 991, 992, up to 999. So it depends on this and this. An interdependent process. Holy moly! You are going to create 6 processes. The first process will drive hex 0. Okay? Position 0. You are going to create another process that will drive hex 1. But it is going to depend on the position 0 process. You will create a third process, but it will depend on the 2 processes before it. You will create a 4th process. It will depend on the 3 processes below it. And so on and so forth. It is actually quite simple. All you do is you just keep adding in an if clause that looks at the digits below it. If the digit below it was a 9, increment. If the 2 digits below it were 9 and 9, increment. If the 3 digits below it were 999, increment it. Okay? So there's two parts. The second part then will actually drive these puppies. Your process is going to obviously produce 4 bits because you need that to produce a 9 in binary. And you're going to use your car decoder again, drop 6 of them down, and boom. When you get this thing running, what you're going to see is this thing will be counting like a clock. But the cool thing about it is you can change the frequency of it to get it to count at either 1 hertz, 10 hertz, 100 hertz, or 1 kilohertz. Okay? You're going to throw the clock on LED 0 just so we can see it blinking, and it's just going to bang. And it's awesome. All right. That is lab 9.4.